All right, well, it's 3 o'clock, so go ahead and start. I imagine there might be a couple more people coming in, but so I'd like to introduce Vadim Sokolov. He's an assistant professor at the Department of Systems Engineering and Operations Research. He has a PhD in computational mathematics from Northern Illinois University. He got that in 2008. He spent about 8 years at Argonne National Laboratory as a principal computational science in a transportation and computing division. He also spent a few years as an instructor at the University of Chicago teaching in the master's in analytics program. And he's now an assistant professor with us. His research interests are in Bayesian statistics, intelligent transportation systems, and machine learning. And he has 21 journal publications. Of these, 13 were published while he was at Mason, and he's got about a little over $1 million in his funding share for research at Mason. And he'll probably say a few more, elaborate a little bit on those things, but I'll give it over to Vadim.
Thank you, John, for the introduction. And I'd like to start by thanking my colleagues from SUR who helped me during the process of preparing the dossier and preparing the presentation, specifically Carla, John, and Paula, who is not here. Quick agenda, so I'll start with one slide summarizing what I've done at Mason over the last 3 years, just in one slide, just a bunch of numbers. And then my background, so what I did before Mason, my education and my work at Argonne at U Chicago. We'll spend maybe 5 to 7 minutes on teaching, and then I'll go to my current research here at Mason. I will highlight one specific project on uncertainty quantification, and then we'll have one slide on the future and the summary slide, and we'll have a Q&A session. Hopefully we'll have enough time for having a session. So here's a quick summary. As John said, I spent 3 years at George Mason, joined 2016 after 9 years at Argonne. During my 3 years at Mason, I brought 6 competitive grants and contracts from a variety of agencies, including NSF, Department of Energy, U.S. Department of Transportation, and Air Force. The total value of those grants and contracts is $1.3 million, and my responsible share, my personal share, is a little bit above $1 million. From those grants, I supported 3 Mason PhD students, 5 master's students, and 1 undergraduate students. My PhD student, Laura Schultz, won Eisenhower Award from US DOT. That's a very prestigious award. Comes with $50,000 for tuition and travel. I think she's probably the first Mason student who won this award. And it usually goes to civil engineering, so we're kind of an outlier in this world. So it was very nice. It was very nice for her to win this. And my work I'm going to present on uncertainty quantification. This is work that is done with Laura Schultz, the PhD student, and the award actually was given for this work. And at Mason, I published 13 papers and 6 conference papers, peer-reviewed conference papers, and 6 out of those papers were with my advisees, students I supervise. And I gave invited talks at conferences and seminars at departments. My teaching rating is 4.72, which is the median, and 4.61, which is the mean, and you see the trend is actually up. I developed 2 new courses and redeveloped 2 other courses, and of course I spent significant time in service. I've been on 14 SUR and VSC committees. When you put this number, it was a little bit shocking to me, but and another highlight, I'm a member of National Academy of Science TRB Committee on Transportation Networks.
The PhD students, have they graduated?
So I have 1 student who is to graduate next semester.
Okay.
She's pre-defending in February.
Okay.
Yeah. And one of the reasons she cannot graduate early is because of the award that requires her to stay a certain period of time. So quick self-identification, that's who I am. I think this is the first time I'm doing this, by the way. That's a very strange experience. So I'm a data scientist, and I specialize in Bayesian statistics, optimization, and computing. And I apply those techniques to applied engineering problems. And I worked on agent-based modeling, and I worked on inverse problems. And one of the things I'm known for are use of deep learning and nonlinear Bayesian filtering for traffic flows tracking and accident identification. And I also pioneered the scalable and integrated supply domain agent-based models that are quite often used right now in practice. So this is work done at Argonne, and this is work that was mostly done here at Mason. This is quickly on my training. As John said, I come from applied math background. Both my undergrad and grad was in applied math. When I worked at Argonne, I took PhD courses from UChicago in statistics, so I have some formal training in statistics as well. And I spent 9 years at Argonne, 2007 to 2016. 1 year was a research assistant, so I was a PhD student working at Argonne. And after that, I was hired as a staff scientist and spent years as a staff scientist. And by the time I was leaving Argonne, I was principal computational engineer. So that's pretty much the highest ranking you can go as an engineer. The next level is a managerial position. During my years at Argonne, I spent also 3 years at UChicago. I had a joint appointment with UChicago's Computing Institute, and I also was a lecturer there. And when I looked at this lecture title, it looked diminishing, but Barack Obama also was a lecturer at UChicago. So just to give you a sense that they don't, he was a lecturer when he was a senator, he was teaching law school. And in 2016, I joined SCOR. Okay. Since I spent a large chunk of my career at Argonne, I'm gonna spend maybe 5 to 10 minutes talking about my Argonne work, just to give you a sense where I'm coming from and how this brings me here to my Mason work. So I'm just gonna give you one example per slide. This is my work on GRID. GRID is the modeling tool that analyzes life cycle of a fuel. I'll give you an example of what life cycle is. If you look at electricity, it seems like it's zero emission fuel. But if you look at the life cycle of electricity, if it comes from coal, it's actually much worse to use electricity in a vehicle than gasoline. So this is a very simple example, but we analyze pretty much 30 different fuels and hundreds of different ways of producing those fuels. It's a lot of data collection and analyzing and putting software together that does this analysis. This is a quote. It's an integral part of mission of the DOE, Department of Energy's Bioenergy Technologies Office, key tool for analysis sustainability. And also our work in GRID appeared in the University of Chicago Discoveries That Changed the World. That's maybe a little bit overstatement. They celebrated 125th anniversary in 2015, and they put this list together, and GRID appeared in this list. So I was the lead developer for the new generation of GRID tool. GRID tool has been around for a while. I was hired to basically revamp the tool and develop the new version of that tool. Evacuation Simulation, this project was funded by DHS. I was a PI on this project. $3.5 million was given to us to optimize operations of emergency managers in the city of Chicago. So emergency managers have a very limited set of resources, people and cars and barriers they use to block the roads. They want to know what's the most optimal allocation of those resources when something happens. So we calculate what's the most optimal allocation, we gave it to them, and they actually changed the evacuation plans as a result of our analysis. Transportation simulator. While working on the evacuation project, we realized that there are no good simulators that can give you a good understanding of transportation systems and not flexible enough. The existing ones are not flexible enough. So I actually led a proposal to US DOT that was eventually funded to develop new generation of transportation simulators, and we called them Polaris. And it was a $2.5 million project at Argonne, and I was the lead architect for Polaris, and I was a co-PI. And the way it works for Argonne, scientists usually co-PI, so you understand. The PI is the manager. So co-PI doesn't mean I played a secondary role. It means that the manager was basically point of contact, but all the technical work and all the day-to-day work has been done by me on this project. Okay. And then at some point, I realized we are in DOE lab, Argonne, and so we can do something with energy. So I wrote an internal proposal with my colleague from the energy group, and we proposed putting transportation simulator and an energy analysis simulator together into one modeling framework, and we got this internal funding. And we finished this internal project at 2016, right before I left to Mason. And I visited Argonne last week, actually, and this little project grown into be $7 million a year program at Argonne, and they have 7 staff scientists working on this project. So it's something that was very small when I left, grew into something very big and sizable. And another evacuation project that I started at Argonne and continued here at Mason, it was $2.9 million funded by USDOT. It was project on optimizing transit operations. So transit agencies want to know something happens, what do we do with schedules? How we rearrange the buses, allocate them to different routes, and how we change the frequencies of the services of different routes. So there was a lot of Bayesian modeling happening here on my side. 240,000 of that was transferred to Mason, and it was pretty much at the tail or the end of this project when I moved. And this is the only project that I moved from Argonne to Mason, so everything else that I've done here was new funding on projects that I knew. And here's the summary of the projects that I have done at Argonne. So as I said, I had 6 competitive grants and contracts, and only one of them was transferred from Argonne. The rest of it is new work. This is copy-paste from my CV, so I'm not going to go through one by one. You can just look at them, but you see that I have NSF. This is together with the List Miller hooks from civil engineering. I have another DOE grant, and this one actually is not connected to Argonne work anymore. This is completely independent of Argonne. This calibration of large-scale transportation simulators, that's what I will highlight a little bit later in my talk. I picked up some work with Bill Roiting. He's doing this modeling project on basically revamping the whole communication system for the Air Force. So I'm just a team member. I didn't write the proposal in this case, but the rest of the cases I did write proposals. Even this grant that was transferred from Argonne, I was the PI back to Argonne. So it was proposed that I wrote, it was competitive proposal, it was BAA that came from USDOT. And this is a pipeline of what I have right now, which is pending, that has not been funded. It has been recently submitted. We have this proposal for DOE led by University of Texas in San Antonio. It's a large $70 million proposal, and Mason is one of the few key partners. Paul, actually, on the Mason side, is the point of contact and leads the whole communication. And I'm leading one of the technical areas under this proposal, which is uncertainty quantification in the manufacturing quality assurance processes. And another project that we recently submitted on money laundering from DHS. No traffic engineer in the loop. This is my career that is still pending. I submitted it this summer. Substance disorder patient transition. This is NSF proposal submitted with colleagues from social work and mathematics, and this is a list of the people I'm working on those proposals. So as you can see, my portfolio starts deviating slightly from transportation, but I still use the same core tools that I have: Bayesian optimization and machine learning and computing. So all of those things go here. So my core mathematical tools are used in other applications. Again, a little bit more of numbers. 21 journal publications over my career and 22 peer-reviewed conferences. I haven't updated this slide. I was hoping it to go to 600, just nice to show 600 number, but it was 599 as of last week. I think they update on Tuesdays, I realized. Actually, Google Scholar updates on Tuesdays every week. Anyhow, and as you see, citation counts, this is 2016, that's when I started working at Mason, and it's basically weekly ramping up. The reason for that is because Argonne was not very encouraging for publishing, and actually it was kind of a side product, and was considered as a very poor investment of your time, frankly speaking. No, that's exactly how they framed it. So our goal was to solve hard problems that require research, but at the end was solution of the problem that was important rather than publications of those solutions. So, but I was able to move to academia and was able to publish in academic journals, and actually in top academic journals, and those papers do get recognized and have visibility in the community. And I gave 38 invited talks and colloquials and conferences. Here are a couple examples. This year I gave the plenary talk at Bayesian inference and stochastic processes, one of the main international meetings on stochastic processes, and I was invited to give a plenary talk there. And next year I'm going to give an invited talk at joint statistical meeting. This is the main statistical meeting. And I also get invited to transportation conferences and OR conferences, so my work is recognized across multiple different communities. And again, the example of my service, the member of Transportation Network Modeling Committee of the National Academy of Sciences Transportation Research Board. Okay. And I will spend 10 minutes maybe on my advising and mentoring and teaching. Here's again a quick summary of my record of advising and mentoring. I supervised 4 PhD students when I was at Argonne, and so you understand the context, the way it works at Argonne. We have this summer or semester-long programs when PhD students come to Argonne and they work with one of the Argonne researchers. And usually they cut the piece of their PhD research and they say, okay, on this piece of research I'm just going to go and work with one of the Argonne people. And sometimes they're funded by Argonne, sometimes they're funded by their home institutions. Inside Argonne we have those educational programs that will subsidize sometimes. So I worked with 4 of those PhD students from different universities across the country, and we published 2 papers with 2 of those students, and all of them are graduated by now. At U Chicago, I supervised 8 master students. I will show you one project that we did with them, and we actually was able to publish IEEE ITS paper in one of them. Projects in IEEE ITS is the journal with highest impact in the transportation field. So if you believe in impact, then that's probably the top journal if you measure by this metric. Supervised 3 master students at Mason and have 1 published paper with my master student, and I supervised another student, PhD student. He left for business school at Texas A&M, and it actually was me who advised him to leave. And I think it's a better place for him. Currently I supervise Laura Schultz, the person who got the Eisenhower Award. Her pre-defense is scheduled for February and defense for the May of 2020. We published 1 paper. We have 1 paper under review and 2 papers under preparation. I also have 1 PhD student that I'm supervising on the NSF project. Liz Miller-Hooks is a co-supervisor. I have 2 master students, and currently I'm recruiting 2 more PhD students who are supposed to come in spring 2020. Last year I recruited 1 PhD student, but she deferred the admission. She had a lot of debts. She said she wants to go and work for a year and then come back for a PhD program. So that's the arrangement. And as I said, the Laura Schultz, the Eisenhower Award, that comes with $50K for travel and stipend. There's supposed to be an image here, and I'm not sure why it doesn't show. I apologize for that. This image actually does show. Anyhow, I'll just show you the video. Let me give you the context. So this is one of the master's projects I did with my U Chicago students. We had Detroit Lions, an NFL team. They were one of the first to adopt dynamic pricing. And they came to us and they say, people don't buy our tickets and we have to arrange the prices in the correct way. And they asked us how to arrange the prices. So U Chicago made a nice video about this project.
A team can predict price demand for any given football season, or any given game, for any given seat in the stadium. As it stands today, franchises are struggling to adapt to the growth in secondary ticket markets like StubHub and SeatGeek. But by utilizing analytics methodologies, University of Chicago students were able to help establish a framework for variable and dynamic pricing models that may allow one NFL team to optimize the ticket prices for future home games. The preliminary goal was to examine whether relationships existed between ticket prices on the secondary market and variables such as opponent, seat section, weather, and Vegas betting line. Students gathered data on past ticket sales from...
So I'll stop here. I'll move. They wanted to understand how to price each specific seat for each specific game. So they wanted very temporal and spatially detailed analysis of the pricing data. And we went back to them, we submitted a report in June 2016, and we told them that we suggest that some areas of the stadium were priced efficiently, and some were underpriced and overpriced. And we told them exactly which areas were underpriced or overpriced. And on February of 2017, so beginning the next season of NFL games, this was written in the web portal, Detroit Joke City. Detroit Lion tickets will cost a little more on average for 2017, but some areas of the stadium will decrease or hold steadily. So they did exactly what we told them to do, even though they wouldn't admit that. So they basically took the report and they said thank you, and the next thing we know, they implemented it without giving credit to anyone. But that's fine. This is an example of a project with master students here at George Mason. We work together with BMW and Connected Signals, Connected Vehicle Company. We analyzed the impact of information provided to drivers. So the projector is bad here. But what you see here, it's a BMW dashboard. It has this little screen. And it shows you that you're approaching the traffic signal state is green, and there's 28 seconds left in this green state. So that's information you get from your dashboard. And we wanted to assess the impact of this information driving behavior, because cities are afraid that people start driving more aggressively. The moment you start seeing 5 seconds, your immediate reaction is to speed. So we did the whole life cycle of the project. We designed the experiment, so we told them how many people to be participating, how many people to have the system on, how many people to have system off, at what times, at what locations. So we did the full design of experiment. They did this experiment in San Francisco. There were 500 drivers that participated in the experiment, and then we analyzed the data, we made the conclusions, and they used this paper. This paper was published in IEEE ITS conference, which is the top transportation conference for connected vehicles. And they use this paper now to go to cities and try to tell them that yes, our technology works and it's valuable. Okay. Quick summary of my teaching at Mason. So I've been teaching 4 different courses. 1 undergraduate course, 1 master's level course, and 1 master's/PhD course. Okay. And you can see the ratings. The red ones are the new courses. I introduced the course in deep learning. This is one of the first universities to teach a course in deep learning. Now it's coming, and I think a lot of the other schools start adapting and teaching on this topic. And I was teaching predictive analytics for master students, so this is mostly for the analytics students. They take the analytics and engineering degree. And again, the red ones are the courses that I developed, and the blue ones are the courses that I significantly modified. And you see my instructor's rating, and there is trend to go up. I had this year that didn't look that good. I had an Iranian TA, and it was, you remember the ban? And TA disappeared at some point for 2-3 weeks. He was writing petitions and participating in riots somewhere.
That was a master's level course?
It was master's level course.
You had 72 students?
Yes, yes.
Courses like that in our school?
Some, yeah. So,
Okay.
yeah, so it was particularly bad setup because I had 72 students, TA who disappeared, and I had to manage a lot of things myself, and I was behind on a lot of things. And actually, if you read the complaints, that's what students complained about, that TA was not there. Anyhow, but if you look at my latest ratings, they're way above that number. All right, some summary of real-world impacts of my work. Polaris, the simulator I developed, is the default tool now for US DOE for assessing energy impact of new transportation solutions. As I said, it's a $7 million a year program now at Argonne. GRID is the default tool for USD for analysis of new transportation fuels. A lot of the policy actually is made. So whenever DOE tries to decide whether to incentivize specific transportation fuel, like to give you 7,500 credit for your electric vehicle, this analysis is based on, the analysis they use to come up is based on this GRID tool. City of Chicago has changed the evacuation plans according to outcomes of our optimization tool. Detroit Lines adopted pricing changes that we proposed. Tools for uncertainty quantification that we're developing here at Mason are being adopted by US DOE now for their analysis. And we're currently discussing with US DOT potential adoption by the cities and planning organizations. And beyond DOT and DOE, our work at Mason has potential to change the way transportation models are used across the world, because transportation simulators is not the only thing that US uses. It's actually used across the world. Every large metropolitan area will have one of those simulators, and they need to know how to optimize them, and that's exactly what we're doing. Now I want to dive into this specific project, uncertainty quantification for transportation systems. I will spend a few minutes highlighting that and giving you a little bit more details so you have a feel of the type of work that we're doing here at Mason. Here's the motivation. Every metropolitan area in the United States of population more than 50,000 has a transportation simulator in place. Okay? And that's how planning organizations make decisions about whether to build a new bridge or not to build a new bridge. So the way it works, there's a pot of federal funding, and the city says, I want a chunk of this funding. And then the federal government says, what are you going to spend it on? And they say, we're going to build a new bridge. And then federal government says, okay, go and do analysis. And so planning organizations do this type of analysis, and they use simulators to do the analysis. And the simulators work. They introduce the new bridge into the model, and they're mainly interested in two metrics: how congestion changes, so travel times on the network, and how emissions change. So do we pollute less or more? Okay? And they come up with those metrics using the simulations, and they go back to federal government, and they say, okay, based on the simulator, it's a great idea to build a bridge. And federal government says, yeah, that's a great idea to build a bridge, here's the money. Okay, so money allocated based on those simulators. And the transportation modeling work is not just the simulator. So simulator is part of the story. Second part of the story is the optimization algorithm. And there are several ways that optimization problem raises in the context of transportation modeling. And in terms of the simulators, we have good simulators now. We have simulators that can accurately predict the flows and emissions on the transportation networks. They can accurately assess the impact of big infrastructure projects. So, and my work contributed, so Polaris simulator that I worked actually contributed in this line of research. But now optimization algorithm, we're actually in the Wild West. People don't really know how to optimize on top of those simulators. They don't really know how to calibrate those simulators. And if you read the reports by planning organizations, it's going to be actually page after page how they manually tweak the parameter of the simulator so the results of the simulator matches the reality. And this is the problem that we're trying to mainly address: how to calibrate those simulators, how to make sure that the parameters match the reality. And the problem is the very same flexibility that simulation models makes them appealing also comes hand in hand with optimization problems that are intractable. So calibration is a specific example of an optimization problem. Problem of calibration is to find values, input values for the simulator, so that the outputs of the simulator match the reality. And the reality is measured flows. So you can measure flows of passengers on transit vehicles or on transit stations, or you can measure flows of cars. You can just put a sensor on the road that counts the cars, so you can put a camera that counts. There are many ways to measure what happens on the real life networks, but we have the real life measurements and one simulator to match them. Okay? And this is 2019 Chicago Metropolitan Agency report that says this year we focused on calibration of selected submodels. So what this statement tells you, we don't really know how to calibrate the simulator. We know how to tweak parameters of some parts of the simulator, and we go and manually do that. So this is state of the art. And by the way, Chicago MPO is one of the most advanced in the country. So you understand where we stand in terms of the practical application of the optimization algorithms. So it's an important problem. Agencies spend several $1 million every year recalibrating those simulators. And there are several hundreds of those models in place across the world. So this is potentially a very large and important problem. And the techniques that we develop here, our Bayesian uncertainty quantification, dimensionality, hopefully is a solution to this type of the problem. Okay, so it's basically black box optimization. We have inputs, we have simulator, we have outputs. And inputs can be, for example, preferences of travelers for transit versus highway travel, or how they value their time, or how they're willing to pay tolls. So a lot of things we don't really know. We cannot measure preferences of travelers that go on the transportation. And the outputs are the flows, basically congestion patterns on the network, or how many people take the bus. Okay, and this is one of the simpler version of the calibration problem. So you have your simulator F, you have measurement Y that comes from the field, and you want to find the parameters that govern your simulator, so that the difference between your simulation and the real world data is as small as possible, and you have some norm that measures it. There are more terms in this, but this is good enough to understand what is happening. Okay. And just to give you a sense of the size of those problems, Detroit has 28,000 road segments, and it has 15 million trips that happens in one day. And population is around 5 million people. So it's a very large problem, and each run of the simulator takes a few hours to a few days, depending on how high of fidelity you want to simulate. So they're very slow to run. And what we do, instead we use fast evaluate Gaussian process surrogates that approximate the simulator. So one thing that we do is we take the simulator and we approximate it with mathematical model. It's a statistical model actually that takes input-output pairs and tries to predict what happens. And we use Gaussian process, which is particularly flexible approximator. And those Gaussian approximations are quite widely used in approximating different transportation problems, or actually in transportation were the first, but in other engineering problems it has been used before. And there are two types of problems. So even though Gaussian processes are very flexible to approximate the simulators and make computations fast, but they fail to learn partners in high dimensions. And I'll show you an example of this type of failure. And even if we can build a Gaussian process surrogate, solving the optimization problem is still an issue. So we take our simulator out, we plug in Gaussian process, and then we solve the optimization problem, but it still becomes an issue in high dimensions, even if you have this very fast approximator to the simulator. So what we need to explore this high dimensional space without having any insights on the problem structure. And for those of you who do optimization, when you have convexity, you have gradients, and that gives you the structure of the problem. In a lot of mixed integer programs, we also look at the problem and we try to extract some structure from it and make solvers to solve it fast. We have good solutions for Cheryl's problem just because we can utilize the structures that are present in the problem. But in this case, there is nothing to look at. It's a black box. You cannot really write down a sequence of equations and try to analyze what kind of structures are present there. So we have to deal with a situation when we cannot assume any structure and we cannot learn any structure by just staring at the problem or try to find a dual of this problem or any other ways that we typically apply to analytical optimization problems. Okay. And here's an example. This is a benchmark problem from the simulation community. It's a simulator of contamination concentrations in the radial waste disposal. And we have inputs which is just some physical parameters: hydraulic conductivity, dispersivity, volumetric distribution, porosity. And then we use Gaussian process to try to approximate the simulator. And what you see here is the true value that comes out of the simulator. And what you see here is y hat, the predicted value from the surrogate. And you see that the only thing that surrogate was able to learn is the average. So it learned the mean, which is not very helpful. And this blue bar shows you uncertainty intervals, so 95% confidence interval. So it's very honest about, I didn't learn much, I just learned the mean, but I actually can quantify how I'm uncertain about what I've learned, so it gives you this very wide uncertainty intervals. So it's a benchmark, and it's only 20 dimensions, so it's not that big of a problem. It's an old simulator, 20 dimensions, and Gaussian process, which is very flexible, fails on this problem. So, and again, and even if you can build a Gaussian process that doesn't fail, it's still hard to explore inputs in high dimensions. As I said, we don't really have any structures to rely on. That's the problem. We cannot look at the problem and try to guess what kind of structures we can utilize. So complexity school will tell you just go and sample randomly. And that's from complexity point of view a very good approach, but from algorithmic point of view a very poor approach. Sampling randomly those spaces, you find nothing. Okay, and we've tried, we did try those. And then if you have small number of parameters, you can actually cover your space, search space with a grid, and can evaluate a simulated every grid. But in even in 20 dimensions, like in our simulator before, even if you can run it in 1 second and you want to try to cover with 10 points per dimension, then you'll need 3.1 trillion years of CPU time to evaluate your simulator at all of those locations. So randomly sampling or covering your space with grids is not an option in this case. So without gradients, we need to exploit those special structures, which, as I said, we don't really have.
Just a second. You said that there are e to the power of 20 directions. Are there physical directions? How do you find directions here? What is direction in your?
So in two-dimensional space, direction is basically going to be a vector.
A vector, yeah.
A vector. So if what I mean.
But you have to have some definition because you can make as many directions as you want, as few as you want. I mean, what is the difference?
Definition is 60 degrees, at least 60. So
okay, all right, okay.
Yeah. So that's what here, at least 60 degrees.
All right.
Yeah. So in 2 dimensions, there are 360. There are going to be 6 directions that are 60 degrees apart from each other.
Yeah.
And in high dimensions, you basically So, and that's how we check for optimality. The way you check for optimality, you say, I'm going to move a little bit here, see if this solution is different. I'm going to move a little bit here. So if you try even checking, that's a very hard problem, and even in 20 dimensions. So here are some existing solutions, and some people who sit in this room actually work on those problems. And solution is just to assume some structure about the simulator. When you're in this high-dimensional space, you have to assume some structure. And so people did this additive model, so you have tried to build additive, assuming there is no correlation structure between input variables, different sampling routines, variable selection, meaning that instead of dealing with this high dimension, I'm going to stare at my inputs and I say, most of them are irrelevant, I'm just going to get rid of them, and I'm going to focus on 3 inputs which I think are the most relevant, and just going to optimize as a function of those 3 inputs. So that's called variable selection and variable screening. Single index means that you say, I think that most of the changes in my output is going to be along specific vector in my input space, and I'm just going to explore this one-dimensional subspace, which is designed by this dot product. Okay. Partitioning the input space, and I will Chan worked on those problems. You basically assume I'm going to cut my space, and I'm going to build a different model in different subparts of the space. And hopefully the structure in these partitions is going to be simpler, and I can utilize some structure. Maybe I can build a constant function or some sort of that. Multi-fidelity, it's also a couple people, Jay Zhu and Edward Huang, work on this multi-fidelity simulations, and there is a professor from MIT, Carolina Zori, she does this multi-fidelity simulations for transportations, which is a good approach. The problem in transportation that building those simulations of low fidelity is still a lot of work. Multi-fidelity means you build a simulator that is, you can run it faster, or maybe it has lower dimensionality, but those simulators still a lot of work to build. So in transportation, it means you have to hire an engineer who builds this simulator, and it actually becomes an expensive problem to do. Active subspaces, again, they assume that function is close to constant along certain directions. 2010 was the solution proposed. We tried most of those techniques, and they didn't work for our problem. Okay, so I'm going to show you what did work for our problem. Our approach is build a surrogate in low-dimensional space. So instead of trying to exploit the original structure, we find a different representation of the original input space by taking some nonlinear transformations. And we want to find good nonlinear transformations that go from original space to some what we call latent space, or space of features. And if you think about a nonlinear machine that does that, the neural networks is a very natural choice. They're very flexible learners, and they can find very complex relationships, and that's what we've used, and this is the setup for our problem. So we have some function that we want to optimize, and instead of building the surrogate phi, first we apply this psi, which is dimensionality reduction, and then we build surrogate in this low dimensional space. And then we say, by combined dimensionality reduction and the surrogate, we want to approximate the function that we're trying to optimize as close as possible. So that's the setup. So we have this function psi that goes from original dimensionality d to lower dimensionality n, and then we have this function phi that approximates the function that we're trying to optimize L. So this goes from this low dimensional space of size n to the real number, and we try to combine those to get the function that we want. And in our case, this psi, the dimensionality reduction, is a deep learner. So it's a neural network that finds those low dimensional representations. And phi is, again, our Gaussian process, the same Gaussian process people have used, but just we build it in a different space. There's no general theory how to choose low dimensionality size n or functional form of phi. And this is a general problem for neural networks. It's not just us. There's a lot of people who spend their time trying to come up with answers to those questions. But it is what it is right now, so theory is behind, but those things work. So in our case, we wanted something that can perform, and it happened to work in our case. So our contribution in this case was finding new architectures that find these low-dimensional spaces, finding optimization techniques, how to deal with constraints, because we have some constraints in how we can construct. Plus, we developed software infrastructure that already been used to target super performance computing for DOE analysis. So our software is already in place and used for actual analysis. I'm going to skip theory. This is not my result. So I'm just going to show you, this is a quick outline of what we're doing. So we have this original space, then we find deep learning projection, and then in this lower dimensional space, we build the surrogate and we approximate the function. Okay. So that's a very simplified version. I mean, our architecture is much more complex. We have loops there, and we have deal with constraints. But this is probably, I was told this is as much of details as I can show in this presentation. I had much more complex version. I was just thought, actually, I was told that it's not a good idea to show them. Anyhow, so we apply our approach to this problem of radio waste disposal modeling. And this is the original Gaussian process that we're trying to feed in data. And this is Gaussian process, that's our dimensionality reduction. And again, this is why this is the prediction from our surrogate. This is the true values, and y hat is the prediction from the surrogate. And you want those points to be close to vertical, so 45-degree lines. And it is actually, it's in this world, it's considered to be a very good approximation of this very complex problem. And our uncertainty intervals are much more narrow now, and they're actually meaningful. So for each point, they have a very meaningful interval. So Gaussian surrogate works. It does the approximation for the mean. It does gives you meaningful confidence intervals. So it becomes a usable model now in this low-dimensional space. Okay. This is another example from the community. This is a wing weight example. The red lines is the prediction that comes from our approach, and the blue lines comes from this active subspace, which is considered to be state-of-the-art in the dimensionality reduction world, and we can outperform the state-of-the-art on this benchmark problem, which is also, this is 10-dimensional, but still considered to be a hard problem in the simulation community. I'm not sure what happened to the presentation. So here you're supposed to see results for transportation problems. And I'm just going to tell you what the results are. We also outperform active subspaces, the state-of-the-art techniques. We can find better solutions, and we can find them faster. Okay, so far our results are empirical. We show that we can solve those complex problems that people were not able to solve before, and we can solve them for transportation simulators, which is a large and important problem for a lot of the cities. I'll spend maybe a couple of minutes highlighting some other projects here at Mason. A Bayesian analysis of passenger flows. This is funded by US DOT, and this is work that was done by Tuan Lee, my PhD student, and we collaborate with PACE. It's the largest bus system in the country, and UChicago and UC Irvine, and the goal was to infer the passenger travel. So we still work on this project, and we wrapping up the paper in it. Another example of my collaboration with Bates & White, an economic consultancy firm. We predict the demand and prices in electricity markets, and we were the first ones to use deep learning that combined with extreme value theory, which is a statistical techniques to model peaks, because in electricity markets they're interested in peaks, and apparently in neural network or statistical models that were traditionally used cannot model those peaks, and we were able that we can combine with extreme value theory to model them, and it was quite successful. Driving behavior, this is collaboration with Nexa. It's a dashcam app. If you go to New York and you get a Uber in Manhattan, every driver will have a Nexa app running it. So they have, in San Francisco is the same story. So they have a lot of users around the country. We analyzed their data set trying to cluster drivers in different categories. They took outputs from our analysis and they went to insurance cars, and they're trying to sell them as a product now. I don't think we're going to get out of it, but we got the good paper in ITS magazine, which is a good, again, a very good transportation journal. Reinforcement learning for last mile derivative. This is the latest project that I started actually this year. So we're looking at how to incorporate complex uncertainty models into behavior of shippers and receivers. Current approaches are limited to very specific probabilistic models of those uncertainties. Approaches like robust optimization, or distributional robust optimization, or stochastic optimization. And we try to use some algorithms from computer science, like reinforcement learning. And it's a collaborative work with Elise Miller-Hooks and Grubhub, which is a Chicago-based company. Thanks to Carla for connecting us to Grubhub. And this is work with Azadeh. Azadeh just started this semester working on this project. So this is going to go for another 2-3 years. A quick list of things that I'm planning to do in the future. So short term, I want to wrap up the calibration work and want to prepare training materials for city planning and agency models. We want to continue talking to DOT and start implementing our techniques in transportation agencies beyond DOE work that is already relies on our work. In the midterm, I have a few ongoing projects that will take, I guess, significant amount of my time that has been already funded. Reinforcement learning for last mile delivery, and right now I'm working with DOE on vehicle control problems that will require the same techniques that we use for last mile problems, and certainly quantification for robotics, manufacturing, and cybersecurity. And this is some of the proposals that I put together with my colleagues from Mason. And in the long term, I want again to diversify even further. I want to still stick to Bayesian statistics and machine learning and computing, but expand to new areas of application. Specifically, I'm interested in expanding to healthcare and digital advertisement. The methodologies that I work on are relevant to many hard optimization problems that exist in healthcare and digital marketing, and there are no good solutions also available for some of those problems. This is a quick summary, and I will open after this for question and answers. So I work on operations research and statistical techniques to solve important, complex, and practical problems. I have several success stories thus far, both at Argonne and here at George Mason. My work has academic and real-world impact. I have a strong publication record, funding record, and advising record. There are many unsolved problems to which my work is of relevance, and I said I'm trying to expand to some of those areas. There's substantial demand, as I said, in healthcare, last mile delivery, digital marketing, and this demand is actually growing as simulation algorithms and optimization algorithms and learning algorithms become better and better and better. My plan is to keep expanding to those new areas while expanding my collaboration with my amazing colleagues. That's it.
So we have time for questions, and if you could try to repeat the question so that
I will.
It probably has a better chance of being heard on the audio.
So recently there was a discussion between myself and some machine learning people who said it's really strange if you ask a combinatorial optimization algorithm, if you ask the people who sell combinatorial optimization algorithms to test various input parameters to indicate for this structure of problem what works best. They try them one at a time, and they say, oh, you probably should use this, this, and this. And he said, and you're part of the combinatorial optimization community, and there are combinations of input parameters that probably work differently than they work singly. Mm-hmm. Why don't your community ever do any machine learning to learn that process? Have you ever considered, since you talk about optimization and machine learning, actually using machine learning to improve current optimization algorithms?
It's actually exactly the conversation I had at Informs last week. So I met my colleague who works on Turing salesman problem. He was quite known actually for solving large-scale problems. And I told him, oh, reinforcement learning will just take over. And I said, no, don't, not so fast, not so fast. He said, 60 years of research, hard to beat, and I agree with him. It's hard to beat 60 years of research. But he actually said the same thing. I think he said tweaking hyperparameters of the optimization solvers that's where machine learning is very valuable. And this is actually the first time I thought about this, and now you're reinforcing that statement.
So we're doing reinforced learning on what you should be doing.
Of I should be doing, and I agree with you. And as you said, a lot of the, when you see computer science publications, they claim that reinforcement learning will outperform anything. And instead, when operations researchers do the same thing, their conclusions are much less optimistic. And they are probably right. And I think I agree with you. I think using machine learning to learn how to parameters.
The warning is that where people want to do this is on optimization problems that take a long time. But in your beginning slides, you indicated these simulations were taking a long time.
Yes.
So I think there's I think people are afraid to get into it because just to do a run to get the output that you're going to need to learn from takes time.
And that's why, so last week we started moving our algorithms to high-performance computers. So because Laura needs to graduate, so we have to speed up the calculations. Yeah. So basically, access to high performance computers is one of the ways to deal with that, which we have started doing already.
In this kind of work, I don't understand it very well, so maybe you can educate me a little bit. Are there any metrics or any ideas of how good can the answer be before you get it and see how close to the answer you get?
So in transportation modeling, the gold standard is a prediction. So everything they care about is prediction. How well your simulator can predict the actual flows on the network. So they actually have a very good metric. And which means that if we go to planning agency and we say, give me a simulator and tell me how well it predicts. And they will give us a number, that's how it predicts on each of those metrics. And then what we'll have to do to show that it's valuable, to go back and find the parameter values that actually lead to better predictions. And once we go back to them and say, we can do much better than your standard model that's in use right now, that's what will be convincing argument for them to say, yes, this algorithm works.
You just said finding the right parameter values, right?
Correct.
Are there any parameters out there that might not be known and might help these things? If some smart person defines a parameter that captures some other aspect of the problem.
That's true. There is a range. So there is a parameter that we know for sure, like day of the week, season. So
rain or
yes, yeah. Okay. So those are fixed. Yeah. So we call them certain parameters. Yeah. And then there are uncertain parameters. That's what we care about. Yeah. Parameters that came from behavioral survey. Okay. How you feel about using highway today? So you get some answer, but the models, when you feed, you can explain only 30% of the variance in those answers. So there's still a huge amount of variance that is not explained by the models they use, and they don't really know how to improve on that. Okay. And among these uncertain parameters, there are two sets. One set, engineers would say, I can give you a range, and it's going to be a very narrow range in which this parameter will make sense. And for some parameters, they say, I can give you a range, but it's going to be a very wide range. So they truly, even engineers who've been doing it for many years, don't have a good idea how to set up those parameters. And so when they do calibrate them, they go and calibrate parameters that they somehow know how to calibrate, and some parameters they don't really know, and they just try to live with that.
All right, thank you.
Great presentation. So I'm also not in this field, but I want to ask you a general question. So when you do these predictions mathematically, I understand the big picture. Where I'm getting lost in these transportation models, being a civil engineer, is how do we I understand part of the parameters being calibrated, but overall, how do we validate them, and how do we, for example, based on the models, we say, okay, based on these certain conditions, this afternoon the model predicts that I-95 is going to be jammed, right?
Yeah.
Before it happens.
Yeah, yeah.
But it doesn't, for whatever reason. So how do we ever validate these predictions?
So there's FHWA manual. It's 700 pages that exactly answers your question.
Okay.
So I'll try to answer it in 1 minute. Okay. So you basically have a region, and there are multiple ways to validate. So one way is basically you pick specific locations, okay, and you calculate travel time between those locations. Some sample of locations in the region for which you have measurements. So let's say this is I-66, and we have good measurements on I-66. We know how much it takes from Fairfax to DC, okay? So we're going to say, and what they do, they actually most of the time they do averages. So they say average is 45 minutes. Then they go to simulator. Simulator actually gives you uncertain outputs, but what they do, they fix the seeds, and they pretend that it's a fixed outcome. And simulator says 55, okay? And they'll do it for multiple paths on the network, and then they average across them, and they say this is our average error, simulation versus. So that's one way. Another way, then they do it by highway, by facility type. So they can do separately for highways, for arterial roads, for sometimes for local roads you don't have real-time measurements, but you have those black tubes, annual counts. So they will compare annual counts versus the counts that comes from the simulator. So depending whether you look at arterial road or highway road, there's going to be different measurements that come from the field, and you will use those measurements differently in your validation process. So.
So I guess by a related question. So you have the function, the y hat, and so before it was just giving an average with the range, and then and then you have a better one, but it still has, you know, quite a bit of range. It
Yeah.
doesn't look that much like a line. So what benefit does it translate to in terms of the final accuracy of?
So dimensionality that we deal with, so I showed the example of 20-dimensional simulators. So dimensionalities we deal with hundreds of parameters. So in 100-dimensional case, if you try to feed Gaussian process, it will do the same thing as it did for radio waves disposal. It will give you the mean. And we were able to go to, right now we do 9-dimensional cases. In 9-dimensional cases, you start seeing the same picture when your Gaussian process actually start giving you some meaningful, it started to define meaningful patterns. And once you have a meaningful patterns, you can start doing the optimization. So you actually know, you have your surrogate tells you, and when we do optimization problem, by the way, we look at two things. We look at the mean value and we look at the uncertainty. So we have the sequential design of experiment. If you have some areas of your outputs that have high uncertainty, those areas will correspond to specific regions in the input space. So your sequential design of experiment procedure will tell you, go to those parts of the input space and sample with high density there. And so the goal of the sequential design of experiment is to find good solutions to optimization problem while also minimizing the uncertainty. So once you say this is a good solution, you want to be more certain about this statement, and the way you become certain is by sampling around this solution. But also what might happen, let's say this is your mean function, right? And you try to minimize it, and you can say this is my best, but then your uncertainty can be like this, right? So it can be from here to here, this specific location. So then your algorithm can say, okay, maybe you should go and sample here because there is 95% chance that no, not 95, but there's a chance that your solution might end up being lower, and your true function happens to be like this. So there's balance. It's basically exploration exploitation balance when you try to feed. We feed the surrogate while sequential sampling the input space. So we solve optimization problem, also try to minimize the uncertainty at the same time.
Question, I'm not sure it makes sense, even that when I was a student many years ago, 5 years ago, I had the stochastic period, which vanished, but I did maximum likelihood estimate with only 3 parameters in, but it was very non-convex, and I solved it over and over again, and every time I got different solutions. But what was remarkable, that if I plugged, the parameters were different, but when I plugged it into the predictions, they were remarkably the same. Have you seen anything like that, or?
We haven't done that. So the way we've operated so far is that we get solution that's better than everybody else can get and claim success.
Yes.
So we haven't explored this, and you're right. The problems we deal with is very non-convex.
Yes.
We'll see the same phenomena as you've seen. The moment we start at a different location, our search process, we likely to end up with a different set of parameters.
Yes, but then how will their prediction differ?
This one we haven't checked.
Yeah, I think it will be interesting to look at.
But also in our case, as was asked, we actually have, on some parameters we have pretty tight constraints, box constraints. So we only have very narrow.
No, mine was unconstrained.
Yeah. So which means that once you put those constraints, you might see a little bit less of this variation or different, solution types. But even within these constraints, I think we will see this phenomena, but we haven't explored that. But it's a good insight.
The function form of psi that you said is still not very clear. People don't know what they use. Is there any guidelines from your work on?
That's exactly what we do. We found architectures that give you a good low-dimensional representation for the simulators that we work with. So we have some rules of thumb that came from this work. And in terms of the dimensionality of each of the layers and how loops are represented, So we've played with a lot of the architectures. And
pinpoint anything. I mean, you said something that's better than the other, or just that more or less?
Well, one thing we realized, before we reduce the dimensionality, we have to expand. So that's the one thing that we learned. So our first layer in the neural network, we go from 100 parameters to 1,000 parameters. And then in this expanded dimensionality, we basically shrink like 1/3. So we go to 300, and at the end we go to 9 of those parameters. So that's one of the insights that we've learned so far, which I think is a little bit counterintuitive, because in a lot of the actual because in computer science applications they try to do the same. Essentially, neural network is dimensionality reduction machine, but they haven't, we haven't seen those type of effects. When you expand, you basically find better low-dimensional spaces and then shrink from this expanded space. So that's an example of insight that we found while.
But experimentally, you're saying that it works. Good.
Yes. Yeah.
Any other questions? Thank you.
So